Good day, everybody. You are welcome to the manual design training. In this class, we are going to consider the design of slab analysis and design. Before we go into the design, I want us to have a look at the design information. In the design information, you are going to have the client, the architect, the designer, the site where the structure is to be erected, then the professional, who is of course a civil engineer that checked the structural design. You are going to have his name under here, checked by. Also, what is the intended use of the structure? That will be stated in the design information as well. Also, the relevant codes that were used for the design. Everything has to be stated in the design information. Also, you will see the design stresses for the concrete and for the steel. Then the fire resistance. How long do we want the structural members to resist fire before we are able to put the fire off? This is the fire resistance. So in this case, we are going to consider 2 hours for all the structural elements. Also, what is the soil condition? In this case, we are going to consider our soil bearing capacity to be 150 kilonewton per meter square. Also, you are going to see the general loading conditions: the live load, the roof load, the finishes, the wall and rendering. These can all be found in the in the design information. So now let's start. We are going to start with slab analysis and design, like I said. And this is the architectural plan. In this lesson, we will not go into the general arrangement preparation. I want to assume all the participants know how to prepare the general arrangement plan. So in this class, we are going to go straight to the point, and we will be starting with the design of a slab in 2-way direction. Now we are going to start with the design of a typical panel 4. Panel 4 is on the grid line B prime to C. You can see B prime to C and 1 prime to 3. B prime to C and 1 prime to 3. We can trace this location on the architectural plan. So let us go to the architectural plan. This is the architectural plan, and panel 4 was extracted from this area. Remember, panel 4 is around B prime to C. This is C. C is along this line, can you see? And B prime is along this line. This is B, so this is B prime. That means panel 4 is within this line and this line. Also in the vertical direction, as you can see from this general arrangement, panel 4 is just starting by the side of this void. This void represents the staircase area. As you can see from the architectural plan, this is the staircase area. So panel 4 is starting from here up to this grid line 3. Can you see? So therefore panel 4 is from this point to this point, and also from this point to this point. This simply means this wall and this wall are directly on panel 4. So now let's go into the design. The first thing we are going to do is to extract this panel, and we are going to have something like this. Therefore, the long span of panel 4 is 5395 millimeter, and the short span, or you say the shorter side of panel 4, is 3950 millimeter. So the next thing we are going to do is to calculate the ratio of LY to LX. I will come back to this span effective depth ratio later in this lesson. So what is the ratio of LY over LX? The ratio of LY over to LX is just the division, just divide the LY by the LX. How I'm going to have this value, and this value can be approximated to 1.4. Now the ratio of our LY to LX is 1.4. Now, just the way we were taught then in school, we were taught that once the ratio of LY to LX is less than or equal to 2, then we should design the panel as two-way. Or when the ratio of LY to LX is greater than 2, then we should design such panel as one-way. This is very, very wrong. This is very, very wrong. I repeat. Because if you are used to this, your design might not be economical. You might end up wasting reinforcement unnecessarily. Now, the general idea is that once the length of your shorter span is less than 3.6 meter, such panel can economically be designed as two-way. However, when your panel has a shorter span greater than 3.6 meter, then that panel can economically be designed as one way. Now looking at this panel 4, the shorter span is 3.950, while the longer span is 5.395. Going by this theory, this panel can economically be designed as a one-way spanning slab. Designing this panel as a two-way spanning slab will make us to come up with a design that is totally uneconomical, and we are going to see this as we proceed in the training. So let's continue. Therefore, we are going to design this panel as both two-way spanning slab and as one-way spanning slab, just to establish the theory that says when the shorter span is less than 3.6 meter, you economically design as two-way, or when it is greater than 3.6 meter, you design economically as one way. So let's proceed. after we might have gotten the ratio of Ly to Lx, then the next thing is to assume a suitable depth for the panel. We can assume the value for our H, or we can assume the value for our effective depth D. D is our effective depth, while H is our overall slab depth. The C you see here is the cover to the reinforcement. Let's have a look at this. The cover to the reinforcement. Let's say this is the detailing of the panel under consideration. In this class, we are still going to treat structural detailing properly. So just for now, let's just take a look at this sketch. Let's say this is a detailing of this panel 4. So the cover we are talking about is the distance from this reinforcement. This circular shape represents the bottom reinforcement, that is B1, while these other one represent the top reinforcement, which is B2. So the distance from this B1 reinforcement here to this place is the cover to the reinforcement. I hope that is clear. So now, how do we get the cover to our reinforcement? How do we get the cover to the reinforcement? So let's go to the BS 8110. We're going to go to, let's go to a table. Table 3.2. I'm scrolling to table 3.2. We want to get cover for the reinforcement. Okay, look at this table 3.2. We have classification of exposure conditions. So we are going to assume that the exposure condition for our slab is mild. That means the concrete surfaces are protected against weather or aggressive conditions. And this table is going to lead us to another table, that is table 3.3. Then under conditions of exposure, since we have assumed mild for our exposure condition, then nominal cover is going to be 25 if we are considering grade 30. If our consideration is grade 30, that is C30, then if you trace this mild down, up here, then you trace this 30 up here, then we are going to have 25 millimeter as our nominal cover. You can see lowest grade of concrete. Now we don't have a column for a lower grade than C30, so let's just take class 30 as our grade of concrete, even though we are going to use grade 20 or 25 in our design. So now let's proceed. From that table we are going to come to another table, table 3.4. Then under table 3.4 we are going to see fire resistance. Now, how long do we want our structural member to resist fire before we are able to put the fire off in case of any fire outbreak? Now, from our design information, we have assumed 2 hours for our fire resistance. So therefore we are now going to trace these 2 hours. We are going to trace it down to a point where we have continuous floors. This is beams, this is for beams, these 2 columns are for beams, these 2 columns are for floors, that is slabs. Why these other 2, they are for ribbed slabs. Then this last column is for structural columns. So since our fire resistance is 2 hours, we trace these 2 hours down here. under continuous floor, because our floor is continuous. Our floor is continuous. As you can see, this panel 4 is continuous towards this direction. Towards this direction it is continuous, but it is going to be discontinuous along this direction. Can you see? We are having this panel 4 to be discontinuous around these two short edges, and it is continuous along these two long edges. So therefore, from this table we are going to go with 25. Now back to the analysis. Like I said, we can assume a suitable depth for our slab, or we can assume a suitable effective depth for our slab, which is D. Then from there we are going to calculate for H, where H is the overall slab depth. This symbol represents the diameter. This very symbol, it represents the diameter of the reinforcement. So we are going to assume this is the reinforcement, this is the reinforcement. We are going to assume a diameter for the reinforcement. Then after the analysis, if the reinforcement is not sufficient, we can now increase the diameter. But let's see whether the reinforcement is going to be sufficient or not. So from here, after assuming a depth of 150 millimeter for the slab, from there we can calculate our D. Or you can as well assume your D. You can assume a suitable value for your D, that is your effective depth. Then from there you will now calculate your overall depth, which is H. And from here we have H is equal to 120, which is the assumed effective depth for the slab. 25 is the cover to the reinforcement. Then half of the diameter, the assumed diameter, which is 12 millimeter. So from here we are going to have 151 millimeter. So instead of using 151, why not use 150 millimeter, so that we know that okay, our overall depth is 150 millimeter. And from here we can recalculate our D to be 119 millimeter. Now from here we are going to do our loading analysis. What is the value of our live loading? What is the value of our dead loading? For the live loading, we are going to look into a table in the BS code. This time around we are going to check BS 6399 part 1 1996. This BS code is for it is used for to check loadings, live loadings, depending on different usages. So in this case, our structure is for domestic and residential activities, and that is category A, as you can see. And under this category A, we have, you can see examples of specific use. You can see all usages within self-contained dwelling units. And because our structure belongs to this group, we will now go for 1.5, and 1.5 is the uniformity, or you can say uniformly distributed load on the panel. That is 1.5 rather. So let's go back. From here we know that our unfactored live loading is 1.5 kilonewton per meter square. So let's calculate the dead loading. What is the dead loading? Dead loadings are the loadings or the weight of permanent structures, permanent features on the slab. When you talk about the self weight of the slab, that is dead load, because it is permanent. When you talk about finishes and screeding on the slab, those are dead loadings. When you talk of ties on the slab, that is also part of the dead loadings. And remember, we have already assumed a value for the dead loading, which is 1.2 kilonewton per meter square. Then for the service loads, services, we have services like plumbing services, electrical services. We have electrical pipes running through our structural members. Then we need to factor this weight as well, and in this case we are going to assume 0.5 kilonewton per meter square. Therefore, the total unfactored dead loading will give us 5.3, which is the addition of all these all together: 3.6, 1.2 and 0.5. Now the next thing is to calculate the ultimate load on the panel. What is the ultimate load on the panel? This is the formula: F is equal to 1.4 GK plus 1.6 QK. What is GK? GK is the total unfactored dead loading, while QK is the unfactored live loading, which we have gotten to be 1.5. So from here we can now calculate the value of the ultimate loading on the panel. So we have 9.82 kilonewton per meter. From there, remember our panel 4. Remember where we extracted this panel 4. Remember we have this wall and this wall resting directly on the panel. So this wall and this wall are the additional wall loadings on the panel. So therefore we will now calculate these additional loadings. How do we calculate it? It has a formula. You have it: wall loading is equal to the wall unit weight, which we have assumed to be 3.47. Quickly, let me explain to you how I got the 3.47, which is the wall loading. Can you see wall and rendering? We have an assumed value of 3.7. Now let me quickly explain to you how I arrived at the 3.7. Let's go to the calculator. Now the block we are going to use for the construction of this structure, let's say after weighing the block, let's say for the weight of the block we arrived at 25 kilograms, just for instance. We are going to divide the weight of this block by the area of the block. What is the area of the block? The area of the block is just, you multiply the length of the block by the width of the block. So 25, you divide 25 by, what is the width of the block? 0.225. Then you divide again by the length of the block, just a block, that's 0.45, that's 450. Then you have this. Then you can convert this. This is already in kilogram per meter square, so let's convert this to kilonewton per meter square. We divide it by 100, so we have 2.47 approximately. Now what of the plastering, the rendering on this block? So we can take those ones as 1 kilonewton per meter square. After adding 1 to this value, we have 3.47 approximately, and that is how I got the unit weight of my wall to be 3.47. I hope that is clear. Then the wall length. How did I get the wall length? You come to the architectural plan, then you add the length of this wall and this wall together. That is your additional wall loading. That is your wall length. You now come back to this analysis. You input the wall length. Then what is the wall height? The wall height, normally the wall height should be the floor to floor height In this case, we want to assume that our floor to floor height is maybe 3.15 meter minus the depth of our beam. Let's say the depth of our beam, the beam and the slab, they are monolithic, so therefore we just remove the depth of the beam. In this case, let's say 450 millimeter, that's 0.45. Therefore the actual length of our wall is going to be 2.7. that is if we have beam. But in a case whereby we don't have beam, because just like the case of this floor, this very floor is not going to have a beam at the top, so that means this floor, this wall is just going to go all the way and touch the surface of the slab. So in this case, if our floor to floor height is 3.15, let's go back to the calculator. If our floor to floor height is 3.15, all we have to do is to remove the value of the thickness of the slab. If I remove the thickness of the slab, I'm going to have 3 meter, and that is why my wall height here is 3 meters. Can you see? 3 meter. Also, what is FOS? FOS is a factor of safety for dead load, and the factor of safety for dead load is 1.4. Then you divide all these by the panel area. What is the panel area? The length of the panel, which is 5.395. You multiply this by the width of the panel, which is 3.95, and from here you have 2.7787 kilonewton per meter square. Therefore, the total loading on the panel is going to be the addition of the initial loading, which is 9.82. Can you see? 9.82, this value, plus this additional wall loading, which is 2.7787. so the addition of these two will give you 12.5987. Therefore, this is the loading on the slab at every 1 meter. So if you want to interpret this value now, you are going to say, because since we are designing per meter length of the slab, we are going to say the loading on this slab is 12.5987 kilonewton per meter length of the slab. Is that clear now? So that is that. The next thing now is to calculate the moment along the short span. Also, we are going to calculate the moment along the long span. What am I saying? Let's say this is a sketch through the panel. Let's say this is a sketch through the panel. A sketch of this panel 4. Let's say this is a sketch 5395 and 3950. The short span reinforcement is going to be arranged along the shorter span, while the long span reinforcement is going to be arranged along the longer span. This reinforcement is the long span reinforcement, while this other one is the shorter, the short span reinforcement. Now, along the shorter span, we are going to calculate for moment within the midspan. Also, we will calculate for moment around the continuous edges. Remember, if we go to the general arrangement plan, let's go to the general arrangement, you will see that this edge of the panel is continuous. This edge of the panel is also continuous. This is the short span direction. Can you see along this floor beam 008 is the short span direction, while along this area is the long span direction. Also, you will observe that the panel is discontinuous around this area because we have staircase here, so the panel is going to be discontinuous around this area. The panel is also discontinuous around this area. So eventually we will be calculating for two different moments along the shorter span, while along the longer span we will only calculate for only one moment, and that is the mid span moment. So we're going to start with the shorter span. We're going to start with the short span design. So we have a positive moment around the mid span. We also have a negative moment around the continuous edge. We have a positive moment around this mid span along this short span. We have, can you see, this is the short span, so we are going to calculate the positive moment within the mid span along this short span. We also calculate the moment along these edges, So now let's start. The first thing we are going to do now is to get the value of our positive bending moment coefficient. How do we get this value? We will now go to table. We go to a table now in the BS 8110 part 1 1997. So 1997. So we go to a table. We go to a table. We go to table 3.14. Table 3.14. Okay. Table 3.14. Okay, this is a table. Now this is where we are going to get the positive bending moment coefficient. Now how do we get the value of the positive bending moment coefficient? We will come to this point. Where is the table? We come to this column. We locate the value of the Ly over Lx, which is 1.4. Then we will also locate the condition of our panel. And if you look at the panel, you will discover that the panel is continuous along the two long edges, while the panel is discontinuous along the two short edges. Can you see? So we will now locate this condition on this table. So let's look for two short edges discontinuous. This is it. Two short edges discontinuous. Now we will now trace this positive moment at midspan. We will trace it down to where we have 1.4. So let's trace this 1.4 down, trace it down, trace it down. You can see that the positive moment at midspan now, the positive moment coefficient at the midspan is 0.045, while the negative moment at the continuous edge is 0.060. So now let's go back to the analysis. From here now we can now calculate the bending moment, the positive moment. That is the positive moment, that is the bending moment along the midspan. And this is the formula: the positive moment coefficient multiplied by the ultimate loading on the panel, then multiplied by the shorter span of the panel raised to power 2. Then from here we can get our design moment. So from here our design moment is 8.8457. From here we are going to calculate also our ultimate moment, and this is the formula: 0.156 FCU BD squared. FCU is the characteristic strength of our concrete. Now remember, you remember this table 3 points. Let's go to the table. There's a particular table we saw when we're trying to get the value for our cover. You remember that table where we have different classes of concrete? Remember, we could not find a column for our class of concrete. Yeah, this is it. Remember, the lowest grade we have on this table is C30, so we are using C25 for our design. Anyway, we are still safe. No, we now go to, okay, so let's go back to the analysis. So from here, our FCU is the characteristic strength of concrete, and B, remember, our design is per meter length. Remember, when I wanted to interpret the value of the ultimate load, I said 12.5987 kilonewton per meter length of the slab, and that is why our B is 1 meter. Then you convert the 1 meter to millimeter, then we have 1000 millimeter. Remember, D, the value for our D is 119 square. Our D is 119 from here. So now we now get the value for our ultimate moment. Then the next thing is to compare the value of our ultimate moment with that of the design moment and check which one is greater. If the ultimate moment is greater than the design moment, then no compression reinforcement is required. What is compression reinforcement? Compression reinforcement is an additional reinforcement provided around the compression zone of a structural member. In this case, we are considering slab. So this, by comparing the value of the ultimate moment with that of the design moment, we will know whether compression reinforcement is required in the slab or not. So in this case, because our ultimate moment is greater than our design moment, so we say no compression reinforcement is required. And from there we will calculate the stiffness coefficient, which is this. Then from here we can get the value for the stiffness coefficient, and from there we can calculate the lever arm factor, which is this. We have a value for our K, which is the stiffness coefficient, and from there we will now get the value of our Z, which is the lever arm factor. Another thing here is, if the value of your Z is greater than 0.95D, like in this case we have 0.97D, our value is greater than the standard value for the lever arm factor. So therefore we will go with the standard value. But when the value you got for your lever arm factor is lesser than this value, than this 0.95D, you have to go with that lesser value. Do you get it now? But if your value is greater, you have to go with 0.95D. If your value is lesser, you go with the lesser value. So from here, we will now calculate the area of steel required in the short span around the mid span. You know, in our slab, since we are designing the slab as a two-way spanning slab, we have reinforcements along the longer span. We also have reinforcements along the shorter span. These reinforcements along the longer span is going to be parallel to the long span, the longer side of the panel, while the short span reinforcement is going to be parallel to the shorter side of the panel. Can you see now? So now we will now calculate the area of our steel. What is the area of our steel? This is a formula. Design moment, then you divide it by 0.95 FYZ. We know the value of our Fy. That is an assumed value for the characteristic strength of our steel. This value can be gotten from the laboratory when you take your steel to the laboratory for test. So, but for the purpose of this training, we are going to assume a value of 410 Newton per millimeter square. So from here we calculate our area of steel. So our area of steel is 200.8881 millimeter square. So from here we will now go to the provision table. We will go to the provision table. So I'm going to the provision table now so that we can prepare reinforcement for the slab along the shorter span. I'm looking for the provision table. Now. Okay. This is the provision table. You can see areas for bar spacing in slab, walls, and pad foundations. Remember, we assumed 12 millimeter for our slab, and remember for the calculation we got 200.888 millimeter square. So the next thing we are going to do now is to trace the value we assumed for the diameter of our slab to a value that is very close to the area of steel we got in our calculation. So in this case, the closest value we have here is 377 millimeter square, and the spacing for this area of steel is 300. What we have here is spacing. All these 100, 125, 150 down to 300, they represent the spacing of the reinforcement. Now remember, our value should be, maybe the value we are going to choose from this table should be at least a difference of 100 from our calculated value. Are we together? Now there is a clause around here. Though this value is a very good value, this 377 millimeter square is a very good value at a spacing of 300 millimeter square. But remember, all these iron benders we use on the site, they don't even know the implication of all this spacing that we are talking about. So most times experience has shown that when you leave the work to them, they tend to increase the spacing. At the end of the day, you might not have something like, in your design, if you specify 300 millimeter spacing, you can end up having 350 spacing, because these iron benders do not know the implication of increasing the spacing of this steel. So to be on a very safe side, we are going to provide for if 452 millimeter square reinforcement at a spacing of 250, so that in case the iron bender add their own, last everything can still fall back to maybe 275, or some you might have some around 300, but let's just provide the reinforcement at a spacing of 250 so that we can be on a very safe side. And that is why we are going to provide for our reinforcement, which is a Y12 at 250 millimeter center to center, and the area of steel is 452 millimeter square. Can you see this is 452? Now I will advise you to always keep your minimum area of steel provision around this value, because experience has shown that iron benders do compromise spacing for reinforcement because they do not know the implication of increasing the spacing of the reinforcement. So this value is a very good value, at least Y12 at 250 millimeter center to center. We are going to stop here for now. Then in the next class we are going to look into the negative moments around the short span. How do we calculate the negative moments around the short span? Remember, the negative moment is going to be around the continuous edge. Can you see this one and this one? Around the continuous edge of the panel along the short span. We will not have any negative moments around the longer span because along the longer span we don't have any slab here, because let's go to the general arrangement. You can see we don't have any slab here. That means our reinforcement here is going to return. It is not going to continue, and that is why this edge is discontinuous and this edge is also discontinuous. So there is nothing like top bar around here. We only have these reinforcements returning back into the slab around this area, and the same thing around this area. But in the case of the shorter span, the reinforcement is going to go into this adjoining slab and into this other adjoining slab. Then we will now have top reinforcement on our side. We call it T1, or some people they call it top bars. So we will now have top bars around there. So in the next class we are going to consider the design, the calculation of the value of the moment along these continuous edges. Stay tuned and let us see as events unfold. Thank you.